In section 6.4, the book talks about some different ways to decide between what type of technique to use. So let's say I'm focusing overall here on some conditional statement, because that's where we could actually decide between which of these statements that I want to, which of these proof techniques I want to use. So let's say I'm trying to prove some P implies Q. Again, if we're doing a direct proof, we assume that P, and then we show that that leads to Q. So as long as assuming the P is sort of an easy thing to do, showing the Q is an easy thing to do, I'm going to want to do a direct proof. Now, contrapositive and contradiction are pretty similar to each other, but there are some differences. So for contrapositive, remember we're going to assume the negation of Q, and then conclude or show the negation of P. So that's how I do a contrapositive. But for contradiction, I'm going to assume both P and not Q. And then I want to show some contradiction. So sometimes when you're doing these proof by contradictions, the contradiction that you get, maybe the contradiction that you're going to get is you're going to get to not P, but you already assumed P. So then you're going to be like, oh, P and not P, contradiction, done. If you never used P, then all you really did in this proof was assume not Q and produce not P. So really, that was a contrapositive. So sometimes contradictions are secret contrapositive proofs. And if you can write a proof as a contrapositive instead of a contradiction, that's generally better. So we prefer to do a contrapositive. So you really need to ask yourself, right, what's the difference with a contradiction? In a contradiction, I'm also assuming P. So I really need to use P here. Because if I'm not using P, especially if I'm just getting down to not P, then really that's just a contrapositive. So what I want to do is I want to give a statement and show how we can really do that statement 3 different ways and talk about the difference between those. So that's what we'll see in the next couple of slides here. So the statement we're going to consider is the following. Let x be a non-zero real number. If x plus 1 over x is less than 2, then x is less than 0. So if a number plus its reciprocal is less than 2, then that number must have been negative to begin with. That's what we want to show. So first, let's go ahead and do this with a direct proof. If I'm going to do a direct proof for this if-then, again, this let part comes before my if-then, so that's going to sort of be this overriding thing. So I'm going to assume x is both a non-zero real number and x plus 1 over x is less than 2. So let's assume x is in R, x not equal to 0, and my if x plus 1 over x, that was not an x is less than 2. Okay, so now I need to somehow derive that x is negative. So we can go through and think about how we can derive that. I know that x is non-zero, but I don't know whether it's positive or negative. So I can't just multiply through by x here, because if x was negative, that might change my inequality. But I can multiply by a quantity that I know is positive, and I know that x squared is positive. So let's say we're going to multiply by x squared, which is greater than 0. So I multiply through by that. So we have x cubed multiplying by that x squared. So I have plus x is less than 2x squared. All right, it's always easier to show numbers are positive So let's go ahead and subtract that 2x squared over plus x is less than 0. I noticed everything has an x in it, so maybe I can factor that out. X squared minus 2x plus 1 is less than 0. Ooh, I like that. That looks like a perfect square. X minus 1 squared is less than 0. And now I know that my perfect squares, x minus 1 squared, is positive, so we can divide by it. Unless x equals 1, in which case I get 0, right? So we'll consider that case separately. So either I get that x equals 1 or x is less than 0. Now, in the case x equals 1, x plus 1 over x is equal to 1 plus 1 over 1, which is equal to 2. So x can't be equal to 1. Therefore, we can conclude that x must be less than 0. So we were able to start by just with our if. We did some fancy algebra here. We were able to conclude that x had to be less than 0. So I concluded my then. So that is my direct proof. So I encourage you to look over this proof, see what we did, why, and think about, is this a nice proof? Do you like the style of this direct proof? And then we'll compare that to the proof by contrapositive and contradictions. All right, let's go ahead and do this proof by contrapositive here. So I want to assume the negation here. So assume, again, x is a non-zero real number. That's always going to be true. X is a real number. X is not equal to 0, but also the negation of this. So x is greater than or equal to 0. Now, I'm assuming it's both not equal to 0 and greater than or equal to 0. So really, you could say that that's the same as assuming x is strictly greater than 0. Maybe I'll put that in there as an IE. I like to use that, the IE, that Latin IE. That means, like, I think of it as that is. X is strictly greater than 0. Okay, so I'm assuming my not Q. And now I need to deduce that x plus 1 over x is less than 2. Now it's going to be really hard to know where to pull that out from. So I'm going to do some background work over here. So I want to show that x plus 1 over x is less than 2. I'm going to do some steps that are going to help me lead to that. Sorry, I want to show the negation of that because I'm doing a contrapositive. So I want to show that x plus 1 over x is greater than or equal to 2. So let's go ahead and multiply through by x. X squared plus x is greater than or equal to 2x. Sorry, that should be plus 1. Algebra's a little off there. So then again, I get x squared minus 2x plus 1 is greater than or equal to 0. I don't know this yet. I'm just trying to show it, because I'm not allowed to do anything with my p or my not p when I'm doing a proof by contrapositive. So then I get that x minus 1 greater than or equal to 0. Ooh, and I do know that's strictly greater than 0, unless x is 1, so then otherwise it's greater than or equal to 0. So I have a square number, always greater than or equal to 0. So now, x is greater than 0. That's what I'm assuming. And I'm going to start with sort of the thing I got from my background work. So we know that x minus 1 squared is greater than or equal to 0. That's just always true, no matter what x is. So x squared minus 2x plus 1 is greater than or equal to 0. So x squared plus 1 is greater than or equal to 2x. Again, I'm just following my background work backwards. And now, since x is strictly greater than 0, we can divide by x. I needed that x to be greater than 0 in order to do that, because you have to make sure you're dividing by a positive quantity here. So then, oops, don't say divide by 0, divide by x. So I get x plus 1 over x is greater than or equal to 2, which is what we wanted to show for the contrapositive. Thus, using the contrapositive, we can conclude the contrapositive of what we were just showed, which is the contrapositive of the original statement, right? The contrapositive of the contrapositive is the original. We can conclude that if x plus 1 over x is less than 2, then x is less than 0. Done. Okay, finally here, let's do this proof by contradiction. So when I'm doing the proof by contradiction, that's going to allow me to assume both stuff based on my hypothesis and my conclusion. So again, I'm going to let x be a real number, x not equal to 0, and I'm going to assume, for sake of contradiction, p and not q. So assume the hypothesis and the negation of the conclusion. And now I'm allowed to use both of these at once. So before, remember, I wasn't allowed to work with my inequality because that wasn't part of my assumption, but now I can. So we know that x plus 1 over x is less than 2. Did not draw an x there, so let's fix that. We can multiply by x since x is greater than or equal to 0. So I get x squared plus 1 is less than 2x. So x squared minus 2x plus 1 is less than 0. Same basic steps that we had before. I get this square being less than 0. That's a contradiction. So this is a contradiction. We should actually explicitly write that out. Thus, our assumption must have been false. And our assumption was p and not q, which then we know the negation of that is if x plus 1 over x is less than 2, then x has to be less than 0, which is what we wanted to show. So the power of this contradiction is it basically allows us to kind of work both sides at once in a way that a direct proof or proof by contrapositive doesn't. So that is the nice thing about this contradiction. All right, so I've just copied those 3 different proofs we just did onto one slide here. So we've got our direct, our contrapositive, and our contradiction. And I just want you to look through those and figure out which ones you like best, and then kind of compare and contrast what did we do similarly in each of them, what did we do different, and see if you have any questions about that, and we'll discuss those in class. For our final discussion question, let's say we want to try to prove the statement P implies Q. And so I'm trying to start my proof, and I want to know which of these 10 options are good proofs. So can I start my proof by assuming P is true? Can I start my proof by assuming P is false? And so forth. So there's a hint that 4 of these are good. And for each one that's good, I want you to say, if that's your starting point, if that's your starting assumption, which proof technique you're actually using in that case. So think through that, see if you can find those 4 good ones and which technique they go to.